Okay, so our next topic, our next major topic, is we want to extend the idea of integrals, which we already did integrals of 2 variable functions and of 3 variable functions. We want to extend that idea to integrating not over a domain, a general domain in 2 space or in 3 space. We want to do integrals over curves and integrals over surfaces. Those are our next 2 major topics. They're called line integrals and then surface integrals. And we're going to start with line integrals, and for that we need some preliminary constructions. And let us go as far back as discussing what is a curve in general. So remember that, so here's a curve in blue. We're going to call it gamma. So it's just a curve in 3-dimensional space. It can be, of course, done in 2-dimensional space as well. And we denoted our way for encoding curves was by using parameterization. So we described the curve as r of t. This is stuff that we did. I'm just reminding you. So r of t was some function of t, which is called x of t in the I direction, plus some other function of t, y of t in the j direction, plus some function of t, z of t in the k direction. So that's a parameterized curve where t runs between some 2 values which can be infinity if it's not a bounded curve. Okay, so everybody remember this? Good? Okay, and usually we're going to write, rather than I, j, and k, we're just going to write x of t, comma, y of t, comma, z of t. Okay, so for every value of t, we get a point on the curve which we denote by r of t. So this is a general point on the curve, and we can think of it as a vector r of t. This is the point x, y, z, corresponding to t in the sense that the x is x of t, the y is y of t, and the z is z of t. Is that clear? Okay. And here's a point corresponding to the parameter t0. This is a point corresponding to a general t. We can find the vector connecting the 2 points. That's the secant, the vector in the direction of the secant. We called that delta r. And then if we take limits, if we take a limit as delta r becomes smaller and smaller, if we take t to approach t0, then we get the secants to be closer and closer. And in the limit process, what we get is the tangent vector, which looks like this. Remember? Okay, as limit of the secant lines. So there's going to be a secant here, a secant here, and a secant here. And in the limit, we're going to get this red tangent vector. And we calculated and found out that this is precisely r prime at t0. Okay, so r prime at t0, r prime at t0, which is the vector. Let's write it in the other notation. X prime at t0, y prime at t0, and z prime at t0. So this vector is the tangent vector to the curve at t0. Good, everybody? Remember this stuff? Vaguely. It was a while ago. Okay. And how did we get this r prime of t0? So I want to remind that because that's going to be useful. So what we did, let's chop off gamma a bit to get some more space. What we did is we said that we took delta r and divided it by delta t. That was kind of a scaling of these vectors, of these secant vectors, which was a different way of writing r at t minus r at t0 divided by t minus t0. That's the definition of delta t. And then when t approaches t0, what we got is precisely r prime at t0. Okay, so this was the theoretic construction of saying that this red vector here, the tangent, is simply the derivatives of the three functions that comprise the parameterization of the vector, of the curve. Clear, everybody? Okay, so what I want to do now is find a length of a curve. The length of a curve, sometimes called arc length, call the curve an arc and find its length. And that's going to play an important role in constructing line integrals. So let's do that. I'm going to do it rather slowly because the idea is very similar to the ideas that we use every time we do integrals. We define new integrals. So here's a curve. I'm going to make it a bit bigger. So here's a curve. Curve gamma. And I want to find the length of gamma. How do we do things in calculus when we want to find things that we don't know? Okay, by the way, there's one way to do it, but I can't. So you need somebody with long hair. Pull out a hair. Put it on the curve, right? This is a non-calculus way of finding the length of a curve. Do you have one this long? Yeah. Pull it out, put it on the curve, hold both sides, do this, doing, and then put it on a ruler. You have the length of a curve, right? But that's not a calculus-ish way of doing it, right? This is a more hands-on. So how do we do it in calculus? And this should look familiar, the idea. We're going to divide it into sub-curves here, sub-segments. They don't have to be of the same length. We can choose any intermediate points that we wish. And then we're going to connect them by straight lines. Straight lines we know how to measure. Okay? So we're going to connect them like this. One, connect the dots. This is fun. You can do it in your notebooks. Okay, so do you agree that the length of this broken black line is the same as the length of the original blue curve? No, what do you mean no? It's not the same, but it's close, right? It's approximately the same. It's a good approximation. Can we make the approximation better? Yes, we can. How do we do that? We take one that introduces, let's look at this one, for example. This one here, clearly the little black segment is significantly shorter than the original blue one. How do we make a better approximation? No problem. We get rid of this. We introduce a new point here. And now the approximation is a lot better. Do you agree? Okay, and we can do this over and over and over. We can refine the partition. Okay, is the terminology familiar? We can refine the partition and now take this one and break it into 3 intermediate steps. And we get better and better approximations of the length of the original blue curve. In the limit of these refinements, we're going to get the actual length. Do you agree? That's the theory. This is the intuitive ideas of the theory. It's not the formal writing. Let's formalize it a bit, not completely. So this point here corresponds to, let's say, t equals a. This is where the curve starts. And t equals b is where the curve ends. And then we have all these t's in between. Let's call them t1, t2, t3, etc. Okay, so the length, let's say the length of the broken black line, the approximation is what? Is just the sum of all these little black segments. Well, these two were red because I replaced them. The sum I equals 1 to n of the lengths of the little black segments. So what are they? So the length of So what's the length? Let's say this is t, let's call it I minus 1, and this is going to be ti. We're going in this direction. So what's the length of this little segment here? This is precisely the vector which we previously called delta r. It's r at ti minus r at ti minus 1. Do you agree? Right? This is the point on the curve r of ti, and this is the point on the curve r of ti minus 1. Writing just the t's is misleading. Okay? This is not the point t1. t1 is a point t1 is some value between a and b. This is not the point t1. This is really the point r of t1, which is x of t1, y of t1, z of t1, and now t2 is going to have to move. Do you agree? Okay, so calling it t1 is a bit misleading. Is everybody with me? Questions? Say something. Good? Okay, thanks for nodding. I appreciate that. Okay, so the difference between these 2 points, the connecting vector, which is the length of which is precisely these little segments, is r at ti minus r at ti minus 1. Is everybody with me? Good? Okay. Good. So what is this? This I can now rewrite. Sigma I equals 1 to n. Instead of this, we previously called it delta ri. That's the length of that secant vector. And I'm going to divide it and multiply it by delta ti. I can always do that. Divide and multiply by the same thing. Delta ti is the difference in the actual t's. I'm going to erase this because this is confusing. I don't want you to think that this is the point t something. Okay, so this point is r at ti minus 1, and this is r at ti, and this is delta ri, which is precisely this, their difference. That's better, less confusing. This is the right thing to write. Okay, now, so we have this, right? Now, delta ti is just ti minus ti minus 1. It's something positive. I can put it inside the absolute value. It's the same thing. And now I'm going to start to refine this partition. I'm going to break it into smaller and smaller and smaller and smaller segments. And in the limit, okay, and this is not a formal arrow because I'm not formally defining the limit. This is the idea, okay. What does this approach? So if you think for a minute, what we have here are kind of Riemann sums. Riemann sums of what? So what is a Riemann sum? In Calc 1, what was a Riemann sum? Is sum, the value of a function at some intermediate point, times the length of the interval, right? Those were Riemann sums. And as we take the limit, as these delta ti's go to 0, or as what we call as we refine the partitions, make the biggest interval smaller and smaller and smaller. There are various ways of saying it. What we approach is the integral from a to b dt. So informally, the delta ti's become the dt. And what is this function? What does this approach in the limit? Let's go one board back for a second. Delta ri over delta ti. This is precisely the secant vectors, and they approach as we get closer and closer. As the delta ti's go to 0, they approach the derivative. Remember, this is precisely what we did here. So in the limit, what we would write here is the length of r prime of t. Clear? Everybody good? So this is L, the length of the actual curve of gamma. Providing the formalizing all of this actually works. And it works under some goodness conditions that things are nice and smooth and not fractalish and all kinds of problematic issues. Okay? So this is the formula for a length of a curve gamma given by some parameterization. The length of the curve is the integral over the magnitude of the tangent vector. Okay? I want to show you that you actually knew this. At least you knew it in a particular case. You've seen it in Calc 1 for a very specific case. So let's write this. So for r of t equals x of t, y of t, z of t, if this is the parameterization, L of gamma equals the integral from a to b of r prime of t dt. And if r of t is given, if the parameterization is given in terms of a function of one variable, if we're measuring not just the general curve in three-dimensional space, but we're measuring a curve which is the graph of a function, we can do that, right? So if, let's write, if gamma is given by y equals f of x, this just means that the curve we're looking at is not any general curve in three-dimensional space. It's the graph of a function in two-dimensional space. This is gamma, right? So this corresponds to a parameterization. We can say that the curve is parameterized. Then we can write r of t equals, and we did several examples like this, t comma f of t. Right? This would be a parameterization corresponding to this. The y is f of x. Do you agree? And we did examples. We did like t and t squared. Right? And t an absolute value of t. You just get the graph of the function. So if this is the situation, let's see what we get. What is r prime of t in this case? R prime of t is what? 1 f prime of t. Do you agree that this is r prime now? And what would we get for the formula of the length of a curve in this situation? This is if gamma is given by the graph of the function, then L of gamma is the integral from a to b, and this time a and b are simply the bounds on which f is defined, of the length of r prime. What's the length of r prime? The length of this thing is the root of the sum of the squares of the coordinates, right? That's how you do a length of a vector. So it's the root of 1 squared, which is 1, plus f prime squared dt. Do you agree? And this is something that is usually proven in Calculus 1. Okay? That the length of a graph of a function is given by this expression. This can be done in a direct, if you don't remember it, or maybe some of you haven't seen it, it can be done in a direct way without going through the theory of general curves. And what you do there is very similar, a very similar construction, and you use more local arguments. You use Lagrange to do the approximations, and then you get this. Okay, so for the graph of a function, this is the formula. Okay, so let's put some boxes here to highlight the important formulas that we need to remember. Okay. So for a general parametrization of a general curve, this is the length. If the curve, in the specific case that the curve is just the graph of a function in one variable, this is what we get for the length. Okay, let's do an example. Let's do a quick example. So let's look, for example, at the unit circle. Example 1, unit circle. Let's find the length of the unit circle. How do we do the length of the unit circle? So can you give me a parametrization of the unit circle? Well, if you're trying to do it in x's and y's, right, the circle you can write as x squared plus y squared equals 1. But then if you're going to break it, you're going to need to parameterize the top half and the bottom half separately, right? Because there's going to be a plus minus there. But we discussed this. How can we parameterize the unit circle differently? Exactly. So we can, no r, because it's a unit circle. R is 1. So it's just going to be cosine t and sine t, where t ranges between 0 and 2 pi. Remember this? Everybody? Okay, what was the tangent in this case? Well, even if you don't remember, it's easy to calculate. It's minus sine of t, cosine of t. Do you agree? Okay, so what's the length of the tangent vector? It's minus sine t squared plus cosine t squared, all of that, root. That's the length of the vector. So it's sine squared plus cosine squared, which is 1. The root of 1 is still 1. Do you agree? Therefore, what's the length of the circle? Is it clear what I meant to write here? So the length of the unit circle is the integral, t ranges from 0 to 2 pi, of r prime of t, the length of r prime of t, which is 1, dt. And this just gives 2 pi, and we knew that, right? The circumference of a circle of radius 1 is just 2 pi. 2 pi times the radius, right? Okay, good. Let's do another example. Let's look at an ellipse. So suppose our ellipse is, how do we parameterize an ellipse? So I assume you saw some examples like this in your homework, but if not, way of parameterizing an ellipse is just introducing, there's the a and the b, right? An ellipse is of the form x squared over a squared plus y squared over b squared equals 1, right? So the a and the b just show up as coefficients here. So this is a parameterization of an ellipse. Have you encountered this? Did you see? Good. So this would be a parameterization of an ellipse. And again, t is going to range from 0 to 2 pi, right? So what would be the r prime? Let's just write the integral. So the length of the ellipse is the integral from 0 to 2 pi of r prime of t dt. So let's see what we get. So r prime is minus a cosine of t. That's the I coordinate. And then I need to square it and add minus a sine of t, bless you, minus a sine of t, right? Plus b cosine of t, square it, and then take a root, dt. Do you agree? Everybody good? Okay. So let's see what we get here. Integral from 0 to 2 pi, a squared sine squared plus b squared cosine squared root to the power 1/2. So how do you solve something like this? Right? You can't just say sine squared plus cosine squared is 1 because there's the a and the b stuck here, and if they're not both 1, or if they're not equal, then you can't just do it that way. So we need to find the antiderivative, right? We need to find the antiderivative of this expression, plug it in at 2 pi, minus at 0, and that's going to be it, right? Sounds simple. Not simple. Very not simple. In fact, it's not doable in closed form. Okay? So this is one of those functions that does not have an elementary antiderivative. Okay? Big question mark. So it doesn't have an elementary antiderivative. Okay? So this cannot be solved in a closed way. We can't get to just an expression, okay, a number. We're just looking for the circumference of an ellipse, right? And in fact, over history, people really wanted to know lengths of ellipses, because in astronomy, the planets that orbit their sun, I don't know if you knew this, orbit the sun in a path that is an ellipse, where the sun sits in one of the foci. It's not a circle. The Earth does not orbit the sun in a circle, but rather in an ellipse. That's why sometimes it's farther and sometimes it's closer, okay, to the sun. And so people wanted to know the lengths of these curves that are the paths that planets orbit, okay? And they wanted to solve integrals like this, and they struggled with them, and it can't be done. There are all kinds of approximation methods which allow you to get approximations to things like this in general, but it can't be done. There is no closed formula for the length of an ellipse. No such thing. Okay? And integrals like this are a particular case of a big family of integrals similar to this that cannot be solved by the regular Newton-Leibniz method of finding an antiderivative. And they have a name. They're called elliptic integrals because of this specific one that was the most intriguing one, the one they really wanted to solve first. Okay, and I'm talking back hundreds of years ago. Newton. Okay, so no formula for length of an ellipse. For the length of an ellipse. Okay? Are you really sad now? No, come on. So today there are ways of approximating things like this, and that's beyond the topic of this clip, but I think it's a cool thing to know. Okay. So one last thing regarding lengths of curves. You can, of course, do other examples which are solvable. What I want to mention is the following, and this is important in what we do next. So let's look here for a second. Think of how this was stated. For a curve given in some parametric representation, the length of the curve is given in terms of this integral, which of course depends on the parameterization, right? If you take a different parameterization, and we've seen that the same curve can have many different parameterizations, right? You take a different parameterization, you get a different expression here. And, well, hopefully the length is going to be the same, and it is. I'm not going to prove it right now, but it is. It doesn't depend on what parameterization you chose, okay? But there is a specific parameterization which is, in some sense, intrinsic to the curve. And it has a name, it's called arc length parameterization. And I want to introduce that briefly. So remark, the length of a curve does not depend on the parameterization. This is an extra E. I hope I'm spelling this parameterization. Is this correct? Hopefully. Okay. Although a priori it seems like it really depends on it. That's what we're calculating. Okay. And we can define, so if we have a curve, let's say the curve looks like this. Here's a curve, gamma. We can choose a parameterization, which is usually denoted by the letter S to distinguish it from all the different parameterizations T. So we can define a parameterization x of s, y of s, z of s. This is a new parameterization where s is a very specific parameter, where s is called the arc length parameter. And what it measures, so at a given point, this point would correspond to the value s, which is precisely the length of the arc up to this point. That's intrinsic to the curve. It doesn't depend on anything. This is given. You can measure it. Where's the girl with the long hair? Right? So we can measure this in whatever way you want. You can do it by choosing some other parameterization and using that to measure. But this would correspond to the value s. So this would correspond to the value s, where precisely s is the length of the curve up to this point. Okay? So what would this correspond to? Let's say we start here. What s value would this correspond to? Right, this would correspond to s equals 0. And what s value would this correspond to? This would correspond to s equals L of gamma, the length of the entire curve, right? And any point in between would correspond to the arc length until that point, up to that point, okay? S, so let's write, corresponds to S, which is the length up to the point. Clear, everybody? So this parameterization, which is very mysterious, I don't know how to give it in terms of formulas, right? If somebody gives me a curve, I don't know how to write the parameter s. What are the functions? What are these functions? I don't know how to say them. I just know they exist, right? If you give me a circle, I can tell you, here's a parameterization. Cosine t, sine t. That's a parameterization of a circle. If you give me a parabola, I can give you a parameterization. T squared. What would be the arc length parameterization of the circle? You would have to think a bit. It doesn't just show up. You have to calculate. But I can tell you how it relates to any given parameterization. And that's not difficult to write. So if gamma is given by some parametrization, R of t, any parametrization, then S of t, so for a given t, the corresponding S, here's gamma, here's some point which corresponded to some value of t. What would be the S corresponding to this point originally given in t? It would be the integral from 0 to t of r prime of t dt. This is the length of the interval up to that point t. Do you agree? So if this corresponds to some value t, then this is the S it's going to correspond to in terms of the arc length variable, of the arc length parameterization. So this point corresponded to t equals a, right? This corresponded to t equals a. Well, it's not from 0, from a, sorry. This corresponded to t equals a. What is the corresponding S? It would be the integral from a to a, which is 0. That's the length if you just go nowhere. This point corresponded to t equals b, right? What would be the corresponding S? It would be the integral from a to b, which is the length of the entire curve. So the corresponding S would be L of gamma. Clear? And for any intermediate t, you just take the integral only up to t. Clear? Now, so we can, okay. So what is S prime of t? Remember that when we find the arc length according to some parameter, we need the derivative, right? So what is S prime of t? Calc 1.
R prime.
Exactly. Right? Why?
The derivative of an integral is
The fundamental theorem, precisely. The fundamental theorem of calculus tells you that if you take a function and define it in terms, this is maybe a bit misleading. We should have called this differently, right? R prime of x dx or whatever. But it's a function of the upper bound of the integral, right? This t in here is just the integrating variable. We could have called it whatever name we wanted to. But S depends on t, on this t. If you vary this t, you get different values of S, right? So this is precisely by the fundamental theorem, S prime of t is the function that sits inside. Everybody remember that? So it's precisely R prime of t. Okay, so this is by the fundamental theorem of calculus. Okay, and this is going to play a role. We're going to use this later. Okay, so this is how the forgot the parentheses. This is how the arc length parameter relates to any given parameter. And what would be, by the way, the length of the curve, L of gamma, in terms of the arc length parameter. It's going to look a bit silly. Okay, we'll discuss this a bit later when we discuss line integrals. Let's leave it at this. Okay, so is this clear? Okay, everybody good? Okay, so given a curve, it can come with many parameterizations. Okay, some are better than others, and we discussed that. Some could introduce a fake feeling of that everything is a fake feeling of having a point where the curve is not smooth. Remember that issue? That according to the parameterization you choose, the curve can seem smooth or not. The derivative can suddenly become zero at some points depending on the parameterization. So I hope you practice this stuff a bit. That one can work with many parameterization, and it's usually better to think a bit and choose a good parameterization. But this specific parameterization, which is called the arc length parameterization, is useful in theory. Okay, and we're going to see how we use it in theory when we define line integrals. It's not very useful in practice because we don't have a concrete formula for what S is. Okay? Okay, it's only, we can define it in terms of another parameterization like this. Okay, so let's stop here, and in the next clip we're actually going to define what is a line integral.